I want to welcome Miss Lindsay, who is in the Department of Astronomy at Yale University. He's a graduate student. Chris is born in Hawaii, one of the two places in the world that are optimized for astronomy, the other being Chile. And hopefully the goddess Pele, how do they know that Pele doesn't like the telescopes? I mean, she really might, you know.
You don't.
It's
The other mountain blew up.
Yeah, that's right. The other mountain blew up, and it's not that far, although apparently Mauna Kea is not in danger but Mauna Loa blew up. Very exciting for the people who live in the southwestern part of the Big Island, which is apparently where they put all the people on the witness protection program in that south corner, and they've been having to dodge, besides the bullets, they've been having to dodge the lava. Chris uses asteroseismology to study the interior mixing and angular momentum transport processes involved in low mass stars, which you know are the bulk of the stars in the universe, smaller and much smaller than the sun. Understanding what is going on inside of stars requires a combination of data analysis and stellar modeling techniques, which I guess we'll hear about. He was an observer for the Mount Wilson node of the Birmingham Solar Oscillations Network. And, you know, Mount Wilson was George Ellery Hale's great facility for solar observations, starting with the SNO telescope and then the 60 and then the 150 inch. Very much worth visiting if you're in the LA area. And he studied high angular degree solar oscillations with data from the Solar Dynamics Observatory. And he's now in a wonderful astronomy department at Yale. Soon I hope to get your degree and join the ranks of professional astronomers for real. So Chris Lindsay, welcome to WA.
Yeah, thank you so much for that great introduction. And I just want to say, in Hawaii, while I was there, growing up, I went to amateur astronomy meetings as a child, and I have a distinct memory of being 6 years old and seeing Saturn's rings for the first time through a 10-inch Dobsonian telescope that someone set up in the backyard of a elementary school. And I think that may be my first ever memory, but I really do think that, you know, despite dabbling in some other things in college, that's really a part of why I decided to pursue astronomy and astrophysics as my professional career. As was mentioned earlier, I'm a graduate student at Yale University. I'm a PhD candidate, which means I've finished my master's portion. And so now I'm doing full-time astrophysics research. So done with classes, done with teaching. And so now we're doing this. And basically what I want to talk to you all about today is this topic of asteroseismology, which may sound familiar to you because of the word seismology. So if we want to know what the inside of a celestial body looks like, you may wonder how we're able to do that where we only can see the surface. For example, you know, how do we know what the internal structure of the Earth is? I can bend down. So if you ask me, how should we figure this out? You know, I would say get a giant drill and just drill through the Earth and look at, you know, what it's made out of. But it turns out you cannot do that for a variety of reasons. But the closest we ever got was a Russian experiment in North Russia called the Kola Super Deep Borehole. Here you can see it on Google Maps. But that only went about 7.5 miles deep into the Earth's crust. But the Earth's diameter, if you wanted to dig all the way to China, you would have to go about 8,000 miles, which means that we've only really drilled through 0.095% of the Earth. So how do we know that, you know, we live on this thin crust and we have a mantle and we have this outer and inner core that's producing our magnetic field? How do we know all that? Well, the answer is we can look at earthquakes. Oops. Is this going? So we can look at earthquakes. And if you time how long an earthquake wave takes to get to different portions of the Earth after a big event, you can figure out what the different layers are made out of, because sound waves, earthquake waves, take a different amount of time to traverse through different materials. So now we've done this for a variety of earthquakes ever since the 1800s, and we know that we have a solid inner core, a molten outer core, this convective mantle, and we live on this tiny 10-kilometer thick crust. But of course, I'm not in the geosciences department. I'm in the astronomy department. So what does this have to do with astronomy? Well, stars are also made out of layers, and there's a funny thing about stars like our sun, which is that the outer layers are violently convecting. So like a pot of water that you leave on the stove for a long time constantly boils and moves. The same thing happens on the surface of our sun and stars like our sun. So this animation you see in the bottom right is actually very new data from an instrument on the Daniel K. Inouye Solar Telescope on Haleakala in Hawaii. And this is a giant mirror that they point at the sun, which you all know is like quite dangerous and hard to get right, engineering speaking. And it's still in the preliminary stages of being calibrated exactly, because obviously you have massive heat loads, so you have to run a refrigerator on the back of this mirror constantly. But the reason why people wanted to build such an instrument is you're able to get the highest resolution images of the solar granulation, which is the top of these convective cells. So on the parts of this, in this GIF that are kind of smooth, those are the upwelling of convective fluid on the top of the sun. And the black parts are the convective fluid traveling downwards. And those parts are cool, the upwelling parts are hot. But what does this have to do with seismology? Well, this constant bubbling motion actually generates starquakes, or basically earthquake-like waves on the sun. And these waves propagate through the solar structure. And if we measure the frequencies of these waves, we can actually tell something about what our stars are configured like inside of them. So this, on the left-hand side, is a plot of a P-mode propagation wave. So a P-mode is a pressure wave. So it's a sound wave, like the wave you're hearing me speaking to you right now with. But inside of the star, there are two different types of waves that can exist. So P-modes, which are sound waves that I was just describing earlier, but there's also something called G-modes, where the restoring force of the wave is buoyancy or gravity. And so that would be like a wave in the ocean, where the restoring force of the perturbation is gravity or buoyancy. And so depending on how the star structure is set up, these modes of different character exist in different places within the star. And that is pretty cool because stars change shape over the course of their lives. So for example, in this diagram, I'm showing you the post-main sequence evolution of a solar mass star. So our sun is exactly one solar mass by definition. In fact, I've frequently tried to Google the mass of the sun, and it just tells me that it's one solar mass. And so it's useless to me because I want it in grams. But now, of course, I memorize it. Yeah, but after a star like our sun runs out of hydrogen fuel in its core. So right now it's fusing together hydrogen to make helium, similar to a hydrogen bomb actually. But after it runs out of hydrogen and it's just left with helium, the core begins to shrink because it's run out of that energy source. And at the same time, the outer layers of the star begin to expand. So the entire star gets bigger. And so we can see the evolution starts in this bottom left point and then moves up. Do I have a person? Can you see this? Yes. Yeah. So it starts in this bottom left point, and then it moves up as it begins to expand, as it runs out of hydrogen and begins burning a smaller amount of hydrogen in the shell around its helium core. This is called the subgiant phase. But then as it reaches something called the Hayashi limit, it begins to evolve vertically, which means it's getting bigger and brighter very fast. And this part of the evolution is called the red giant branch, which is, when you hear people talk about red giants, like, Betelgeuse and things like that, that's a star that's configured like this with a massive, fluffy, cool envelope around a very hot helium core. And during this phase of evolution, there's a point at which the star's brightness dims slightly before continuing on up. And that's a kind of subtle thing that, it's an area of active research that I'll talk more about in the latter portions of my talk. But for now, all you need to know is this is called the red giant branch luminosity bump. Now, like I was saying about waves earlier, stars of different size will oscillate with different frequency. So a small star like our sun or a dwarf star is like this tiny little trumpet. It will sound very high in frequency. Whereas a large star like a red giant, Betelgeuse, will have a very low frequency. And I actually have some sonifications for you, which I hope don't hurt your ears. So let me just turn this down. So if you hear that, it's at okay, I can't hear it anymore. Okay. So that's the sound of a 1 solar mass main sequence star, which is pretty small. But now let's hear the sound of a red giant. Oh. You hear that? The low rumbling. So a large star like a red giant will oscillate with much lower frequency. Now you might wonder how these frequencies are calculated. Well, it's kind of an interesting process. So if you take a light curve or velocity curve, which is the brightness or the velocity of a star over a long period of time, it shows variations. But these variations are periodic because they're the pulsation modes of the star. And so I took basically 4 years of Kepler light curve data and compressed it into 10 seconds. And that's what you hear for the red giant and the main sequence star. So the main sequence star on average has pulsations of a much higher frequency when compared with the low frequency red giant. And different stars will sound really weird, especially if you have like 2 stars rotating around each other, but I won't show that now. So these modes are described using spherical harmonic functions, which I won't get into, but the point is that you can detect these oscillation modes, which are either radial modes, which means the whole star is expanding and contracting with a given frequency, or just part of the star is expanding and contracting with a different frequency. And we split them up by what's called the angular degree. So an L of 0 mode will be a radial mode, an L of 1 mode will be a dipole mode, an L of 2 mode will be a quadrupole mode, etc. And this is just an animation showing what those spherical harmonic mathematical functions look like on a sphere. But how do we actually observe them, right? I told you we take light curves, but what does that look like? So this is a picture of me during my undergraduate days at the University of Southern California, where I was an observer with the Birmingham Solar Oscillations Network, which is a global network of small telescopes, like commercially available mounts, which track the sun. And basically the idea is to measure the sun's velocity, line of sight velocity, so whether or not the sun is expanding towards us or away from us over a very long baseline. So we can get those low frequency oscillations, high frequency oscillations, we get them all, right? And this is a picture in 2020 of when Mount Wilson was on fire, but now it's actually covered in ice. So, things change pretty fast up there, I guess. But yeah, I agree that if you have a chance, go up to Mount Wilson, it's really cool. So this is one of the data products of the BISON experiment. So basically what we have is the line of sight radial velocity. So whether or not we can see the solar surface coming towards us at, 2.5 meters per second, or away from us at 2.5 meters per second at a given time. So on the x-axis here, it's date, and on the y-axis, it's the meter per second radial velocity of the star. And this data set is very long. The BISON team has been doing this for many years now, but this is just a small chunk. And basically, to look at the oscillations here, we can convert this, velocity curve into a power spectrum, which means you take the Fourier transform of the velocity or light curve. And what that means is that in this plot, we have the frequency of a given oscillation, and then we have the power at that oscillation. So what this plot is saying is that at around 3000 microhertz in frequency, which is about 5 minutes or so, one pulse every 5 minutes, there is a lot of oscillation power at these specific frequencies, which was very interesting. And this was actually discovered on Mount Wilson, back in the 60s. And it was kind of unexpected because, this star is showing harmonics like an instrument would, and pulsing in this very regular pattern. So we can see that there's a comb structure here where these high oscillation peaks are separated by kind of a regular spacing. And that regular spacing is called delta nu, or the large frequency separation, which is actually proportional to the square root of the mean density of the star. So here we have the equation, the scaling relation for delta nu. And we see that delta nu, the spacing between oscillation mode peaks in this power spectrum, scales with the square root of the mass of the star over the radius of the star cubed, which is pretty cool. That means if we can measure the power spectrum, if we just take a very long light curve of a star, take the power spectrum of it, get this delta nu out, we can say something about the density of the star, which, just by looking up at the night sky at the light, how would you say that, oh, Betelgeuse is this massive star that's not extremely massive, but it's very large in radius, versus, what if it's just a main sequence star like the sun that's very close to us? Like, how would we tell that? But this gives you that answer. There's also another thing that's cool, which is the frequency of maximum oscillation power, or nu max. And nu max is a more complicated relation. It depends on the mass of the star, the radius of the star, as well as the temperature of the star. But if we can measure at what frequency these oscillation peaks are like highest, as well as the spacing between oscillation peaks, we have two equations and two unknowns for mass and radius, assuming you have a temperature measurement, which is just the color of the star, right? Blue stars are hotter, red stars are cooler. Then we have two equations, two unknowns that we can solve for a mass of a star and the radius of a star, given this power spectrum, which is extremely powerful, especially for exoplanet studies. So I don't know if you've had a speaker talk about exoplanet research yet, but there's a very popular method of finding exoplanets. It's the most prolific method, which is the transit method, which basically means you stare at a star for a really long time. And if there's a planet that happens to be aligned with your line of sight crossing between the star and the observer, the brightness over time for that star that you're looking at will dip. You can't actually resolve the star and the planet though. So how do you know how big this planet is? How do you know what the radius is? Well, if you know the distance from the parent star to that exoplanet, and you know the radius of the star from asteroseismology, you can actually constrain the radius of the planet, which is really cool. So now we're getting radius values for extrasolar planets, which is pretty wild. All right, but my research doesn't really focus on exoplanets. My research is focused on the individual oscillation modes of many stars. And so how do we convert this peak structure into what the individual oscillation mode frequencies are and what that says about the stellar interior? Well, what we can do is cut this power spectrum into chunks of length delta nu, stack them on top of each other. This is a plot of increasing frequency on the y-axis and frequency modulated by the delta nu value. And we can see that ridges are starting to form. And what do those mean? Well, these ridges are ridges of modes of the same angular degree, L, but of consecutive radial orders. And what this means, essentially, is that I can connect a model of the star, like a theoretical stellar model, to the observations that we're looking at. So this is for the sun. This background shows the oscillation power in that shell diagram that I was describing earlier. And these points show a stellar model, which was made on a computer. And what that allows us to do is basically constrain what the inside of the sun or another star looks like. So what are the different layers of the sun? You can tell that from asteroseismology. And then what are the different layers of another star is also possible using this method. So what I mainly use this for is to look at evolved stars. So remember the plot of post-main sequence evolution as the star gets really huge. So this is for a main sequence star where the P modes are all you see. So all we see for the sun are pressure modes. But as the star evolves past the main sequence, through the subgiant branch and up the red giant branch, modes of mixed character appear. So this is a subgiant propagation diagram and a red giant propagation diagram. So I'm going to attempt to explain mixed modes now. So in this blue region, there exists modes of G character, which means that the oscillation modes are governed by gravity or by buoyancy. Whereas in this orange region, the modes are governed by pressure. But across this white evanescent region, mode coupling can occur. And that basically means that for a main sequence star, the deep internal layers are inaccessible to asteroseismology. There's no modes propagating here at all. And all we can see is down to about 0.1 radii. So this is the radius coordinate, and then this is the frequency coordinate on the y-axis, radius on the x-axis. And so basically underneath, 0.1 solar radii, the star's structure is inaccessible. But in the red giant branch, these internal portions are accessible to asteroseismology because of mode coupling across the evanescent region. And so why is that interesting? Well, I'm gonna explain a very difficult problem that was prevalent for a while, which is the difference between a red giant branch star and a red clump star. So a red giant branch star is a star which is burning hydrogen in the shell, whereas a red clump star is a star that's burning helium in the core. And these are different portions of the stellar evolutionary history, but on a diagram of temperature versus luminosity, they exist in about the same place. So it's hard to disentangle them. But using asteroseismology, you can, because the internals are different. So in a red clump star, it's burning helium, the core is much smaller. Whereas in a red giant branch star, the core is more expanded and it's burning hydrogen. So basically, if you look at the modes, the oscillation modes of two stars that look the same in every other way, same spectra, same temperature, same luminosity, they'll be different in terms of their oscillation modes. I explained how exoplanet studies make use of asteroseismology to get better masses and radii in order to get better masses and radii for exoplanets. And another thing that you can do with asteroseismology is get accurate stellar ages. So in our galaxy, the Milky Way, in the current model of how galaxy formation happens, we start off with a progenitor galaxy, but then more and more small galaxies accrete onto our Milky Way progenitor. And that's how our galaxy got to be so large. And so if you want to figure out what the exact history of our Milky Way is, you need to know the ages of the stars from those dwarf galaxies that are accreting onto our Milky Way. And the way that you do that is you accurately model them using asteroseismology and get their stellar ages. And so stellar ages can decrease the error in an inferred age down to 10% age error, which is really good because if you look at a star, how do you tell how old it is? it's impossible. Even for our sun, we don't have a good constraint from just observing the sun. The best constraints for how old our solar system is come from rocks, from comets. And we look at the rock and we can date the rock, and then we can date the sun. So that's how that works. Otherwise, we wouldn't know how old our solar system is. All right. Basically, what I'm saying is that a lot of astronomy depends on how well we know the internals of stars. And so my first project at Yale, which I'll go through pretty fast because I don't want to get too in the weeds of evolved star asteroseismology to determine stellar structures. But my first project at Yale, which was published last year in the Astrophysical Journal, was using mixed mode observations that's those interior G modes coupling to the exterior P modes, giving us access to the core regions of stars. We were using those modes to kind of investigate the mixing processes at the boundaries of convection zones in stars. So what does that look like? So in a red giant star, there's this massive convective envelope that's bubbling and churning, and there's some sort of boundary layer before you get to the inert core on the inside. So what exactly is happening at that boundary layer is a current unknown in stellar modeling, but it's important to figure that out because at that boundary layer, how you model it will affect everything else about the star's evolution, from how old the stellar model is to at the end of a star's life, whether or not it becomes a black hole or a neutron star or something else. So understanding the internal processes of stars is very important. So I was looking at a process called overshooting, which is basically extra mixing beyond a classical convection zone. And so I was explaining the red giant branch luminosity bump. Turns out if you take data and compare it to where stellar models say the red giant branch bump is, there's a discrepancy. So here we see an overdensity of real red giants that were observed using the Apache Point Observatory. And we see here a collection of stellar models. And we would expect that this overdensity of points matches up with where these models are doubling back and spending a lot of time, right? These are evolutionary tracks. So as the star evolves, it's going up here and then spending a long time doubling back and then continuing going up. And we would expect that there would be more points along these turning back red giant branch bump parts. Turns out if you incorporate overshooting into a stellar model, you can push down where this red giant branch luminosity bump happens in a stellar model, which means that there's some evidence for incorporating overshoot into stellar models from just looking at masses, luminosities, and temperatures of stars. But I wanted to go further, so I made a grid of models which modeled convective overshoot in different ways. Here's an example evolution for a 1.4 solar mass model with different amounts of convective overshoot. So on the top here, we see the hydrogen fraction in the solid line and the helium fraction profile of a star in the dotted line. So here we have the radius of the stellar model, and here we have the mass fraction. And we see that stars with larger amounts of overshoot have hydrogen fraction well-mixed zones that extend further than their no overshoot counterparts. And this connects to the Brunt-Weissler frequency profile, which is basically the boundary of where G modes can propagate, which means that changing this overshoot should change something about the oscillation modes of the star. And that was a hypothesis. Turns out it was true. So with a stellar model, you can calculate the hypothetical oscillation mode frequencies. We found that there was a difference depending on if you are incorporating overshooting in the stellar models. And this was all theoretical work that was published, but the holy grail of this would be to actually observe red giant oscillation modes and place them on a diagram which would in theory constrain the amount of convective overshooting which should be incorporated into stellar models. But turns out that's very difficult. Here we have in a shell diagram, which is like but these are for hypothetical stellar models. So how would we put this in comparison to real data? Well, these are the current fits. So if you fit the hypothetical mixed mode periods using this function, you can back out something called the gravity mode phase offset term, which is, if you are a physicist and have thought about how waves kind of change their phase at boundaries, it's basically the phase offset imparted onto a G mode at the boundary. But what's important is that we see that varying the overshoot changes the evolution of this parameter over the star's life. But there are also, observers, astroseismic observers, which have gotten this value for real stars. But since the errors are pretty high in these epsilon G values for real stars, it's pretty inconclusive as to how well we can constrain the amount of overshoot from red giant convective envelopes. So that was this project. What I want to do is go back to the observations and get real values for the gravity mode phase offset. This will be pretty difficult though, because the sun is our best case scenario. So those diagrams that I was showing of the solar oscillation modes are the absolute most pristine power spectra you could possibly get. Real power spectra don't often look like that. So there's some data processing and kind of signals analysis that I need to perform on Kepler data. So if you've heard of Kepler, that's that space telescope that went up and stared at the same region of the sky for like 4 years straight before its reaction wheel failed and it began spinning around. But thankfully, Kepler had some red giants in its field. So I'm going to look at the data for those red giants and see if I can extract quality oscillation modes to compare with my stellar models. So that's what I'll be doing over the next few years. But at the same time, I'm about to submit a paper on subgiant oscillations. So in the subgiant phase, that's before the red giant phase, the star is kind of in a transitionary mode where processes that were occurring during its main sequence. Let me close this. Yeah, it's okay. This says fossil signatures of convective overshoot. So in a main sequence star, there could be processes that shift material around in the star. And those shifts will manifest themselves in the mixed mode oscillations of subgiant stars, which I think will be observable by using Kepler data. And so I've already done a lot of this work. And basically what this requires is matching up theoretical and model, theoretical, which means model oscillation modes, with the real data. And so I'm pretty proud of these mode matching fits. So these are shell diagrams like I was showing you earlier. And the solid lines are the real observations. And you can see that their error bars are really tiny. So you can see inside of them, they have little dots. Those are their error bar sizes. So they're really good data that we're getting from Kepler. These are obviously the best cases that I could find. But these open squares are a theoretical stellar model that I've created to try to match these oscillation modes. And the fact that this is a good fit basically means that I'm getting the interior structures right for these real subgiants, which is pretty cool because I'm trying to use it to constrain these interior mixing and evolutionary processes that are occurring in subgiant stars. But since the main sequence processes encode themselves during the subgiant phase, it's also helping us constrain some things that should be incorporated into main sequence stellar models. And so that's my research program. I hope that you've all learned something about asteroseismology, and I am sure that I can help answer any questions, because this is quite a difficult topic in astronomy and kind of not a normal thing that astronomers kind of talk about, but it's I think a really important tool for use in this big data age where we need to get good parameters for the stars that we're looking at. It's no longer good enough to just see them and say what color they are and how many they are and things like that. We want to know exactly what's going on inside of them, know their ages, know their masses and radii very well, because those parameters will inform other areas of astronomy, such as how our galaxy formed and how planets form, and is there planets in the habitable zone that life could exist on? All this sort of stuff relies on how well we know our stars. So thank you.
Really good. Thank you.
Larry?
Yeah, so the bulk of the stars that are red are dwarfs, not giants. They are convective.
Yeah.
Primarily, and they also have a lot of flares and other things that make looking for planets around them, for life on planets around them, that's questionable because they're so active. But do the seismic effects in those stars contribute to their surface instabilities and flares, or is it something else?
So the reason why M dwarfs, these low mass, 0.3 solar mass stars, which make up the bulk of the stars in the universe by number, the reason why they're so active and they flare so much is because their convection zones are so strong. They are almost entirely convective. And so there's a lot of material, a lot of charged plasma moving around, which generates these magnetic fields, which are thought to cause these stellar flares. And I am currently mentoring a Yale sophomore on using machine learning to identify flares in the Kepler and TESS data sets. So that is basically showing that for stars that are lighter, that are low in mass, these flare rates, so how many times these flares are happening, it is a lot higher. So there's a lot more flares on these low mass stars. So stars such as AU-MIC, which you may have heard of, which is an M dwarf with a planet revolving around it in the habitable zone, flares all the time. And that would be a real big problem for life as we know it, because extreme ultraviolet and X-rays will do serious damage to DNA. And it's not certain if DNA is like if DNA evolved on Earth or evolved somewhere else and came to Earth. But if DNA is the dominant method of transferring genes in the universe, then that would kind of disqualify some of these M dwarfs from hosting life.
The amount of convection kind of overwhelms any ability of shock waves to act as their own process within.
Yeah, so P modes definitely do exist in M dwarfs, and you can see them oscillating very quickly. But it's I guess less important to use asteroseismology to study M dwarfs, because we know from models of how luminosity is transported through stars that the entire structure of the M dwarf is well mixed, is convective. So the whole thing is like part of that convective pot boiling. There's no layers of radiative zone where the energy is transported by radiation instead of convection. So in our sun, we have an outer layer that's convective, but the inner part is all radiative where mixing doesn't happen.
What is it about white dwarfs?
Yes, that's a very hot topic of research, actually. And white dwarf and actually neutron stars oscillate as well. Their oscillations are different than solar type oscillations that I'm talking about. But it is thought that the oscillations detected for neutron stars and white dwarfs can help figure out the neutron star equation of state, which is currently unknown, and whoever finds it is guaranteed a Nobel Prize. I promise, I'd bet my life on it. And for white dwarfs, it's a problem figuring out the ages of them, because basically you can say that, oh, white dwarfs just cool over time, there's no more nuclear fusion happening, but it's not quite sure how that cooling happens exactly. And then hopefully using asteroseismology, you can answer some of those questions about how old white dwarfs are, which will help you find out how old supernova remnants are, things like that.
Are there any questions on Zoom? Anybody want to just chime in? Sometimes it's hard to tell.
You can ask me about things that aren't asteroseismology too.
One other question with regard to the detecting the periodic swelling and receding of the sun. That's integrated over the surface of the sun. You can see, whereas the first slide that you showed with the anyway circulations, that's happening kind of beneath that in terms of the integrated values that you get for the velocity.
Yeah. So these oscillations do impart velocity on the solar structure. So if you look at the whole kind of power spectrum of the sun, so where is this? So this part right here, the solar-like oscillation comb, is at much higher frequencies. So if you have the oscillation power as a function of frequency, you have a lot of gunk going on here. And this is the signal from the granulation. And then it kind of calms down. And then there are these regular spaced kind of solar-like oscillations, which is what I'm showing here. But here is a signal from granulation. And if you could figure out how to model granulation in stars, there's a lot of money in it because extreme precision radial velocities for exoplanet studies rely on good methods for getting out granulation from stellar observations. So this granulation behavior of this material churning and moving on the surface does cause some problems when you take a long velocity curve and get the oscillation modes. But it's a different frequency regime than these solar-like oscillations, which are literally sound waves that travel through the star. And so, yeah.
Okay.
Another question. I happen to be doing some reading and running a local for a newsletter about the initial solar mass spectrum. And recently that I read talked a little bit about the different reasons why a star at birth might stop accreting material. The question was, when do the oscillations start?
So when a star, so you'll have a core inside of a molecular cloud, and the gravity will kind of overcome the inner turbulence of the cloud. And that process was discovered by an old professor at Yale named Richard Larson. So if you've read about Larson's laws for stellar formation, that's where that comes from, just to plug my school. But when that molecular core inside of the molecular cloud begins to collapse, there'll be a protostar that forms, which is basically heated up by friction of the gas, right? So it's just a hot ball of gas. It's not yet fusing hydrogen into helium. So it falls in on itself, heats up, and then it'll start to ignite hydrogen in the center. And that will be, that's like when the protostar like fully becomes a protostar. And at that point, convection will begin, because convection is basically driven by having a hot heat source underneath some fluid. And so you've all done this at home when you cook. If you cook, I don't, but if you do, and if you have a hot heat source above some fluid, you'll drive some convection, because the heat is transported more efficiently by the bulk motion of material, that's convection, than by just radiation. And so once that hydrogen begins to fuse, that's when you get convection, and that's when you start getting stellar oscillations. But the problem with that is that you cannot see directly the surface of a protostar. It is encased in a cloud of gas and dust, which will be eventually swept away by the light of the star over the course of millions of years, which is relatively fast, astronomically speaking. But you can't see the actual star. So the way that protostellar observations are done is with different wavelengths of light, such as radio. So ALMA does a lot of protostar observations. But even then, you kind of get a lot of the gas in the way. So you're looking at gas that's heated up rather than the actual star itself. So you can't really do asteroseismology for young protostars, but young stars that have swept their gas and dust away, are accessible to asteroseismology. And it's a really important thing because you can age date them pretty well. because as the star kind of contracts and kind of forms into its main sequence phase, this interior structure is rearranging itself, and that interior structure is connected to the oscillation waves.
So we actually have a question from Zoom from John Gale about Betelgeuse. Is the recent dimming episode, do you have any new data on that? Or does that relate to your research at all?
Yeah, so there's like a Twitter account that's like about Betelgeuse, and it'll say like its percentage brightening. And I'm not sure what it's at right now, but I think it's starting to dim again after going brighter than it is usually. And there's like various theories about why Betelgeuse is doing that. I don't know if you've read a lot about it, but there's some theories that it's like outgassing dust as it's kind of dying, because these giant stars actually have very low surface gravity. So the particles on the surface of the star are not bound very tightly to the star itself. So if you think about a black hole and you think about how strong that binding force is that it can suck in light, black hole is tiny. But a star like Betelgeuse, which is giant, massive, fluffy like a marshmallow, it is not holding on to its material very strong. So if it like has an episode where it outgasses or has some dust that forms into the atmosphere, it blows away very easily. And so that's one theory about why Betelgeuse is dimming, which doesn't look good for having Betelgeuse go supernova soon. But who knows? I mean, I can't predict that. It's like predicting the stock market. You can't do it. I think did you have a question? Okay.
Okay, well, if there are no further questions, I'd like to thank Chris for such a fantastic talk.
Thank you for the invitation.